Understanding NumPy's einsum. How does np.einsum work? Given arrays A and B, their matrix multiplication followed by transpose is computed using A at B dot T, or equivalently, using
Note, this answer is based on a short blog post about einsum I wrote a while ago. What does einsum do? Imagine that we have two multi-dimensional arrays, A and B. Now let's suppose we want to multiply A with B in a particular way to create new array of products, and then maybe sum this new array along particular axes, and then maybe transpose the axes of the new array in a particular order. There's a good chance that einsum will help us do this faster and more memory efficiently than combinations of the NumPy functions, like multiply, sum and transpose will allow. How does einsum work? Here's a simple, but not completely trivial, example. Take the following two arrays. We will multiply A and B element-wise, and then sum along the rows of the new array. In normal NumPy we'd write So here, the indexing operation on aligns up the first axis of the two arrays so that the multiplication can be broadcast. The rows of the array of products are then summed to return the answer. Now if we wanted to use einsum instead, we could write the signature string I is the key here and needs a little bit of explaining. You can think of it in two halves. On the left-hand side, left of the, we've labeled the two input arrays. To the right of, we've labeled the array we want to end up with. Here is what happens next. A has one axis, we've labeled it I. And B has two axes, we've labeled axis 0 as I and axis 1 as J. By repeating the label I in both input arrays, we are telling einsum that these two axes should be multiplied together. In other words, we're multiplying array A with each column of array B, just like a column, np.newAxis does. Notice that J does not appear as a label in our desired output, we've just used I, we want to end up with a 1D array. By omitting the label, we're telling einsum to sum along this axis. In other words, we're summing the rows of the products, just like .sum axis equals 1 does. That's basically all you need to know to use einsum. It helps to play about a little. If we leave both labels in the output, A, we get back a 2D array of products, same as a column, np.newAxis B. If we say no output labels, IA, we get back a single number, same as doing a column, np.newAxis B.sum. The great thing about einsum, however, is that it does not build a temporary array of products first, it just sums the products as it goes. This can lead to big savings in memory use. A slightly bigger example. To explain the dot product, here are two new arrays. We will compute the dot product using np.einsum A, jk, ik, A, B. Here's a picture showing the labeling of the A and B and the output array that we get from the function. You can see that label J is repeated. This means we're multiplying the rows of A with the columns of B. Furthermore, the label J is not included in the output. We're summing these products. Labels I and K are kept for the output, so we get back a 2D array. It might be even clearer to compare this result with the array where the label J is not summed. Below, on the left you can see the 3D array that results from writing np.einsum a, j, k, ike, a, b, i.e. we've kept label j. Summing axis j gives the expected dot product, shown on the right. Some exercises. To get more of a feel for einsum, it can be useful to implement familiar NumPy array operations using the subscript notation. Anything that involves combinations of multiplying and summing axes can be written using einsum. Let A and B be two 1D arrays with the same length. For example, A equals np.arrange 10 and B equals np.arrange 5, 15. The sum of A can be written. Element-wise multiplication, a B, can be written. The inner product or dot product, NP, inner A, B, or NP, A, B, can be written. The outer product, NP.outer A, B, can be written. For 2D arrays C and D, provided that the axes are compatible lengths, both the same length or one of them has length 1, here are a few examples. The trace of C, sum of main diagonal, NP, trace C, can be written. Element-wise multiplication of C and the transpose of D, CDT, can be written. Multiplying each element of C by the array D, to make a 4D array, C column, none, D, can be written.
Grasping the idea of NumPy.einsum is very easy if you understand it intuitively. As an example, let's start with a simple description involving matrix multiplication. To use NumPy.einsum, all you have to do is to pass the so-called subscript string as an argument, followed by your input arrays. Let's say you have two 2D arrays, A and B, and you want to do matrix multiplication. So, you do. Here the subscript string ij corresponds to array A while the subscript string jk corresponds to array B. Also, the most important thing to note here is that the number of characters in each subscript string must match the dimensions of the array, i.e., 2 chars for 2D arrays, 3 chars for 3D arrays, and so on. And if you repeat the chars between subscript strings, j in our case, then that means you want the einsum to happen along those dimensions. Thus, they will be sum reduced, i.e., that dimension will be gone. The subscript string after this symbol represent the dimensions of our resultant array. If you leave it empty, then everything will be summed and a scalar value is returned as the result. Else the resultant array will have dimensions according to the subscript string. In our example, it'll be ik. This is intuitive because we know that for the matrix multiplication to work, the number of columns in array A has to match the number of rows in array B, which is what is happening here, i.e., we encode this knowledge by repeating the char j in the subscript string. Here are some more examples illustrating the use/power of np.einsum in implementing some common tensor or ND array operations, succinctly. Inputs. 1. Matrix multiplication, similar to np.matmul R1, R2. 2. Extract elements along the main diagonal, similar to np.diag_r. 3. Atomar product, i.e. element-wise product of two arrays, similar to R1 R2. 4. Element-wise squaring, similar to np.square R or R2. 5. Trace, i.e. sum of main diagonal elements, similar to np.trace_r. 6. Matrix transpose, similar to np.transpose_r. 7. Outer product, of vectors, similar to np.outer vec1, vec2. 8. Inner product, of vectors, similar to np.inner vec1, vec2. 9. Sum along axis 0, similar to np.sum_r, axis equals 0. 10. Sum along axis 1, similar to np.sum_r, axis equals 1. 11. Batch matrix multiplication. (15) Double dot products, similar to np.sum Atomar product cf. 3. 16. 2D and 3D array multiplication. Such a multiplication could be very useful when solving linear system of equations, x equals b, where you want to verify the result. On the contrary, if one has to use np.matmul for this verification, we have to do couple of reshape operations to achieve the same result like bonus. Read more math here, Einstein summation, and definitely here, tensor notation.
When reading einsum equations, I found it the most helpful to just be able to mentally boil them down to their imperative versions. Let's start with the following, imposing, statement. Working through the punctuation first, we see that we have two 4-letter comma-separated blobs, B and BHWJ, before the arrow, and a single 3-letter blob B after it. Therefore, The equation produces a rank 3 tensor result from two rank 4 tensor inputs. Now, let each letter in each blob be the name of a range variable. The position at which the letter appears in the blob is the index of the axis that it ranges over in that tensor. The imperative summation that produces each element of C, therefore, has to start with 3 nested for loops, one for each index of C. So, essentially, you have a for loop for every output index of C. We'll leave the ranges undetermined for now. Next we look at the left-hand side. Are there any range variables there that don't appear on the right-hand side? In our case, yes, H and W. Add an inner nested for loop for every such variable. Inside the innermost loop we now have all indices defined, so we can write the actual summation and the translation is complete. If you've been able to follow the code thus far, then congratulations. This is all you need to be able to read einsum equations. Notice in particular how the original einsum formula maps to the final summation statement in the snippet above. The for loops and range bounds are just fluff, and that final statement is all you really need to understand what's going on. For the sake of completeness, let's see how to determine the ranges for each range variable. Well, the range of each variable is simply the length of the dimensions which it indexes. Obviously, if a variable indexes more than one dimension in one or more tensors, then the lengths of each of those dimensions have to be equal. Here's the code above with the complete ranges.
Another view on np.einsum. Most answers here explain by example. I thought I'd give an additional point of view. You can see einsum as a generalized matrix summation operator. The string given contains the subscripts, which are labels representing axes. I like to think of it as your operation definition. The subscripts provide two apparent constraints: the number of axes for each input array, axis size equality between inputs. Let's take the initial example, np.einsum a, jk, key, a, b. Here the constraints 1 translates to a .num equals 2 and b.num equals 2, and 2 to a .shape 1 equals b.shape 0. As you will see later down, there are other constraints. For instance, labels in the output subscript must not appear more than once. Labels in the output subscript must appear in the input subscripts. When looking at a, jk, key, you can think of it as which components from the input arrays will contribute to component, k, I, of the output array. The subscripts contain the exact definition of the operation for each component of the output array. We will stick with operation a, jk, key, and the following definitions of a and b. The output, z, will have a shape of b.shape 1, a .shape 0, and could naively be constructed in the following way. Starting with a blank array for z. np.einsum is about accumulating contributions in the output array. Each ai, j, bj, k pair is seen contributing to each zk, I component. You might have noticed, it looks extremely similar to how you would go about computing general matrix multiplications. Minimal implementation. Here is a minimal implementation of np.einsum in Python. This should help understand what is really going on under the hood. As we go along, I will keep referring to the previous example. Defining inputs as A, B. np.einsum can actually take more than 2 inputs. In the following, we will focus on the general case, n inputs and n input subscripts. The main goal is to find the domain of iteration, i.e. the Cartesian product of all our ranges. We can't rely on manually writing for loops, simply because we don't know how many there will be. The main idea is this: we need to find all unique labels. I will use key and keys to refer to them, find the corresponding array shape, then create ranges for each one, and compute the product of the ranges using a tools.product to get the domain of study. The domain of study is the Cartesian product, range 0, 2, x range 0, 3, x range 0, 4. Subscripts processing. Find the unique keys, labels, in the input subscripts. We should be checking for constraints, as well as in the output subscript. Using set is a bad idea, but it will work for the purpose of this example. Get the associated sizes, used to initialize the output array, and construct the ranges, used to create our domain of iteration. We need an list containing the keys, labels. Compute the Cartesian product of the ranges. Note, tools.product1 returns an iterator which gets consumed over time. Initialize the output tensor as we will be looping over domain. For each iteration, indices will contain the values on each axis. In our example, that would provide I, j, and k as a tuple, k, I, j, for each input, a and b. We need to determine which component to fetch. That's ai, j, and bj, k, yes. However, we don't have variables I, j, and k, literally speaking. We can zip indices with to_key, create a mapping between each key, label, and its current value. To get the coordinates for the output array, we use vals and loop over the keys, vals key, for key and res_expo. However, to use these to index the output array, we need to wrap it with tuple and zip to separate the indices along each axis. Same for the input indices, although there can be several. We will use tools.reduce to compute the product of all contributing components. Overall, the loop over the domain looks like that's pretty close to what np.einsum a, jk, key, a, b, returns.
If you want to see more, please consider subscribe link.